Let's recall that the derivative of a function f of x at a point A is the instantaneous rate of change of the function at that point. As a limit, it can be expressed like this, which can be interpreted geometrically as a limit of slopes of secant lines. The tangent line of the function at A is defined to be the line passing through the point A f of A, whose slope is equal to the limit, if the limit exists. If it doesn't, then the function has no tangent line at that point. Note that this definition doesn't allow for a vertical tangent line to be a true tangent line. Let's take an informal look at this limit. Loosely speaking, it means that f prime of A is almost equal to the difference quotient. If we rearrange the terms, we get this expression, which means that the new function g of h is almost a linear function in h. But g is just f shifted to A, so this is just saying that near A, f of x is almost a linear function. More formally, if we return to the limit definition of the derivative, we see that this limit must hold, which means that the numerator approaches 0 faster than the denominator. Geometrically, this means that as we zoom into the point A f of A, the function gets closer and closer to its tangent line in such a way that makes it more and more difficult to distinguish between the two. In other words, the difference between the function and its tangent line is shrinking to 0 faster than the width of the zoomed window is shrinking to 0. This is actually a property that can be used to define differentiability, which we'll see in a moment. Let's look first at a standard application of local linearity. Suppose that we want to estimate the square root of 26. We know that f of x equals the square root of x is differentiable on the interval from 0 to infinity, and thus we can approximate its values near any positive value of a by values of its tangent lines near a. Let's let a equal 25. Then for small values of h, f of 25 plus h is roughly h times f prime of 25 plus f of 25, which we can rewrite as h times 1 over 2 square root of 25 plus square root of 25. When we let h equal 1 and simplify, we get square root of 26, approximately 5.1. Of course, this estimation gets better as h gets smaller. Finally, let's look at an alternative definition of differentiability that uses no limits, but rather just local linearity. Saying that a function f of x is differentiable at x equals a means that there's a function phi of x that's continuous at x equals a, such that f of x equals f of a plus phi of x times x minus a. The value phi of a is the derivative of f at a. In symbols, f prime of a equals phi of a. It's worth noting that in general, f prime of x is not equal to phi of x. This definition has several advantages. First, it provides a very good basis for generalizing differentiability to multivariable functions. It also defines differentiability using continuity rather than limits. You might object that we defined continuity in terms of limits, so this definition still relies on them. But rest assured that continuity can also be defined without using limits, even though we won't talk about that here. As one example of the use of this definition, let's show that f of x equals the absolute value of x isn't differentiable at x equals 0. If phi of x is a function satisfying the absolute value of x equals the absolute value of 0 plus phi of x times x minus 0, then phi of x is x divided by the absolute value of x, which is not continuous at 0. So there's no continuous function satisfying the condition for differentiability. By the alternative definition, the absolute value of x is not differentiable at 0. We can also see this by zooming into the point 0, 0. No matter how far we zoom, the graph never starts looking like any line.